In today's video, we're going to be discussing solving higher order differential equations using the auxiliary equation. Now, the auxiliary equation is a method used to solve higher order equations like this with ease. Now, I'm going to be introducing to you different kinds of notation. So, we know dy over dx and y prime. This dy over dx is actually the Leibniz notation. This is actually the Lagrange notation. And one you may not know is y dot, which is the Newton notation. But one you might not know is this, which is the Eulerian notation. So this means the derivative of y with respect to x. And if you want to expand it to the second derivative, usually you could just add something here or you put 2 to indicate second derivative. We also put 2 in here to indicate second derivative, but it looks like that. So how are we going to use this here? Well, mm, we're going to be using the Euler notation in order to solve this differential equation. So let's put this in Eulerian notation. So this is a second derivative, so it's going to be d squared y. Now, what do we derive it with respect to what? We don't really have, we don't really say what it is. We could be x, it could be t, it could be whatever. Let's just put t for now. Minus 6, then d y plus 8y. Since y has no, this one has no derivative, equals 0. Now, we can disregard t for now and just focus on the non-y's. So let's factor out y. Now, this might look a bit weird, but we can factor out y here, and it would lead us to have something useful on our hands. Now look at this. This looks like a trinomial, a polynomial, if you will. And we can treat it like a polynomial, and it will lead us somewhere. So, where would it lead us? In here, we have d squared minus 6d plus 8. We can interpret this as d minus 2 and d minus 4. That is the factorized form of it. And to equate it to 0, d can be 2 or 4. So 2 and 4, what does that give us? Well, it gives us exactly the powers of e that we need in order to get a general equation. So this is going to be the general equation. C1, the arbitrary constant, e to the 2x. This is going to be the first root. And then plus C2, e to the 4x. This is going to be the second root. So if you solve it backwards, if you try eliminating the arbitrary constants, you will end up with y prime prime minus 6y prime plus 8y equals 0. And that's surprising because solving a trinomial will give us the answer. Well, it makes sense. The derivation for this is letting y be equal to some like c e to the ax and whatnot. But you can trust me on this one that we can use the rules of trinomials in order to solve these kinds of equations. Now, this is the general solution. What about the particular solution? We have two parameters here. Y at 0 equals 3 and y at ln2 equals 24. Now, y0 equals 3, it's understandable. We can put it here. 3 equals c1 times e to the 0, which is 0, plus c2 e to the 0, again, 0. Now, for this one, y of ln2 equals 24. Now, what could be e to the 2 times ln2? Well, this could be put as right, that's right, the exponent in the inside of the ln. So this is going to be e to the ln2 squared or e to the ln4. And we know that e and ln can cancel each other out, giving us 4. So it's going to be 4c1 plus This is going to be what, 16 C2. Since 4 ln 2, this will give us ln 16, which is going to be just 16 here. And this equates to 24. All right. We can solve that, or we can use our calculator since we are in differential equations in order to solve that. Give me a moment. According to my calculator, C1 equals 2 and C2 equals 1. You can check that yourself. So, we can replace this general equation to be a more particular equation. 2e to the 2x plus e to the 4x. That's going to be your final answer. Oh, so this is a third order derivative. Now we can skip all the faffle about the d and the d whatever, and let's just skip to the polynomial. So d cubed minus 3d squared plus 4. So how do we solve this in terms of solving the polynomial? Well, usually, if your teacher isn't cruel, he will give you a rational polynomial. Usually, the factors would be plus or minus the factors of the constant, which is 4. This isn't like if you went or if a random stranger went to you and asked you for a cubic, this isn't reliable. But this is a way of finding out if something is true. Let's try negative 1. If we substitute negative 1 into here, we get negative 1 minus, well, negative 1 squared is just 1, so negative 3 plus 4 equals 0. If this and that agree, this means that negative 1 is a root. And indeed, negative 1 minus 3 plus 4 is 0, and 0 is 0. So they agree, therefore, negative 1 is a root. So with that, we can divide this by d plus 1, since we know that negative 1 is a root. We just need to know what else it could be a root of. We could use the synthetic method. Let's do it. So we got 1, negative 3, 0, and 4. The rules are you drop the first one, you multiply it, then you multiply, and then you put it here. So it's negative 1. The 3 minus 1 is negative 4. Put that here, go there. It becomes positive 4. Uh, 0 plus 4 is just 4. Put here, put that there. So negative 1 times 4 is negative 4. 4 minus 4 is 0. So this is going to be the coefficients of what we need. So d squared minus 4d plus 4. So that's going to be the second factor. And d squared minus 4d plus 4 is a quadratic. We can use the quadratic equation, or if you know your if you know your trinomials, we know that this is d minus 2 squared. This is a perfect square. Now this is going to be the second case. The second case is if there is a square in here, because the roots of d is negative 1 and 2. But there's actually another one, and it is also 2. So there's 2 of the same root. So how can that be? Maybe you could say, well, if we apply the things we learned earlier, this would be y equals c1 e to the negative x plus c2 e to the 2x plus c3 e to the 2x. But this and that would be, well, they have the same term. The only difference there is their coefficients, which are arbitrary constants. You can add them together to create another arbitrary constant. So in this situation where you have a square here, or a cube, or a four, or a fourth power, or fifth power, whatever, you put successive powers of x right here. So that is going to be your answer here. Now, for example, maybe you have like d minus 1 quantity 5 equals 0, right? So it's going to be harder, but it's going to be successive powers of x, so like this. So first you set up everything. E to the x plus e to the x. You have to do this 5 times because there are uh, 5 roots of the same thing. Hold on. Okay, so C1 e to the x, no change. So C2, and then we have to multiply it by x since it needs to be different from here. And then here, you need to multiply by x squared. And here, x cubed, and here, x to the 4. So that's how you perform that. Now, if you refer back to the auxiliary equation, you will find that I mean the arbitrary removal of arbitrary constants, you will find that this does result to this. The x just makes it harder to do that because it's product rule and all that, but eventually you will arrive at this answer. So that's how it happens. Now this is for the third case. Hmm. At first, there seems to be nothing wrong with here. So let's try, I don't know any factoring that can happen in here. So let's try the quadratic equation. So again, d squared minus 4d plus 13 was 0. So let's try the quadratic equation. So negative of negative 4 is just 4 plus minus square root of negative 4 squared is 16 minus 4 times 1 times 13 is 52, and there's a problem. 16 minus 52 is negative, and a negative number below a square root means it's an imaginary number. So does that mean we're wrong? No. This just means that this is an imaginary number. We could continue here, so let's continue. Uh, 4 here becomes 2 plus or minus 16 minus 52. Let's do a quick solve of that. It's 36. So that's 6. So it's negative 36 because we're doing that. So it's going to be 6i since it is under the, yeah, under this. Then over 2, of course, because there's over 2 here. So it's 2 plus or minus 3i. So this is going to be root, but how are you going to implement? Is it just e to the 2 plus 3i? Well, not really. Because of a little known fact called Euler's formula, another Euler reference, e to the I theta is cosine theta plus I sine theta. And we can exploit this to our fact here because we are raising e to a complex number which has an imaginary number in it. Remember, an imaginary number, e raised to an imaginary number has cosine and I sine in it as baked in its DNA. So how are we supposed to take care of this? Well, usually an equation like this, it will take of the form 2 plus or minus 3i. That usually is the case for something like this. So what we're going to do is to take the real part first. So y equals e to the 2x, and then since there is a 3 in here, we can put cosine of 3x or t or whatever you want, but we have x here, so we just put x plus sine of 3x. Now we just put the arbitrary constants where it's belong. Now, if you're saying, well, how about the imaginary unit here? Shouldn't there be an imaginary number near sine 3x? Well, yes, but the arbitrary constant means that, well, the arbitrary constant can be any constant, even if it is a complex number. So another way to solve this is to recognize that this is d squared minus 4d plus 4 plus 9. So what happens is this becomes d minus 2 quantity squared plus 9 equals 0. This goes to the other side. So d minus 2 quantity squared equals negative 9. Square root both sides. To get rid of this, we get d minus 2 equals plus or minus 3i. Or d equals 2 plus or minus 3i. So the 2 represents this one. Let me just point it out. It represents this one. And the 3i represent these ones. So that's it. Now, I'm going to have more videos later. So Hang on tight and see you in the next video.